So now we're going to be using the cubic polynomial we found in video 2 for the compressibility factor, and we're going to be using Cardano's formula to find the specific volumes as they relate to the Maxwell construction. So a very simplified version of the Maxwell construction here is that given this line, the equilibrium pressure, there are these specific volumes, and the integrals of this curve evaluated at these specific volumes. So for the first integral will be the first specific volume and the second specific volume. Then the second integral will be the second specific volume and the third specific volume. All it's saying is that these two integrals will be equal to each other. But we don't know those specific volumes yet. So we're going to be coming up with a function that can determine these specific volumes so we can later plug them in and use them to solve for and plot a Maxwell construction. So we can take a quick overview of the Cardano's formula. It's basically saying that if you have this cubic polynomial of this form, using the coefficients a, b, and c, you can do some things, derive some values for q and r here, and then using those values of q and r, and specifically the squared value of r and the cubed value of q, we can determine how many roots there will be, and then also compute the roots using a series of methods. So we can jump right in. We're going to be creating a function that's looking for the cube roots, and we're going to be inputting a, b, and c. And again, these are the a, b, and c from our previous compressibility factor polynomial. We don't need those quite yet. So the first thing we can do is we can go ahead and define q and r. So q is going to be equal to a squared minus 3 times b, all divided by 9. And then our r is going to be equal to 2 times a cubed minus 9 times a times b plus 27c. And I'm going to put some parentheses around these. You don't really have to, but it just makes me feel a little more comfortable with it and helps me divide it up better. Actually, we don't need any. Oh, yes, we do. Forgot to divide by 54 here. All right, and then so since we have a condition here, r squared is less than q cubed, we're going to need an if-then statement. And our first statement is going to be if r squared is less than q cubed, then we want to do that. We want to compute theta using this formula, and then we'll plug theta into these three equations to solve for the roots. So from here, we want to calculate theta, and theta is going to be equal to the arc cosine of our r divided by the square root of q cubed, and we can write this as q to the 1/2, or 1.15, I should say. That's good, and then these will be our roots, but we'll define those in a second. For now, I want to move on, and we're going to do the else statement. I'll give myself some space here. And from here, we want to calculate a, and a equals sine r, and then the term absolute value of r plus the same thing up here, the square root of r squared minus q cubed, all to the 1/3. And one thing to note about this is the sine function here. So if we want to take a look at what the sine function does, all it does is that if you have a negative value, it will return a -1. If you have a value of 0, it will return a 0. And if you have a value that is positive, it will return a +1. So here, we're going to be defining a is equal to the negative sign of r. And again, this is the same r that we have up here. The only difference is the calculations involved after we have our q and r. And then times the term, and then this will all be to the 1/3, so we'll do that now. Then we want the absolute value of r. Plus, and then we want this term here, the r squared minus q cubed, the square root of that. So we'll do the r squared minus q cubed, and we want the square root. So numpy dot square root that, and then that is our a. And we also have this other term b. So we could do an if-then statement for this, but we can say, we'll say b equals q divided by a if a does not equal 0, else 0. So what this is saying is that b is going to be equal to the value q divided by the value a here, assuming a does not equal 0. Else, if a equals 0, then b is going to be 0. So one small note, I did forget an asterisk up here, so I went ahead and added that in. And now we're ready to solve for our roots. We're actually going to be doing the second set of roots first because it's easier. And our root here, we're only going to have one, but we're still going to call the variable roots because we're going to be returning the roots. But our root here is just going to be this x1. We can ignore these x2 and x3 because these are both imaginary numbers and we don't need to worry about them if we're dealing with real substances. So our root is going to be big A plus big B minus our A divided by 3. And then this A is this A that we brought in initially. It has nothing to do with this A that we defined in our cubic ABES. This A is locally defined, so there will be no issues there. There would be an issue if we were to define A somewhere outside of either of these functions, but we haven't so far, so we're good to go. And then our roots for our first set of equations are right here. And we can notice that these terms here are all the same, and then this term here is all the same. The only difference is the input to the cosine function. So we can actually do this all in one go instead of having to define 3 different functions. And we can say -2 times the square root of q. And then we'll ignore this cosine function real quick because we still have this similar term down here. And then minus a divided by 3. And we can go back and add in our cosine. And the term changes for each of these. So we're going to actually set this up as an array. And our first term will be theta divided by 3. Our second term is going to be theta plus 2 times pi. And then that divided by 3. And then our last term is going to be similar. It's going to be theta minus 2 times mp pi divided by 3. So now when we calculate our theta and all that, it will actually give us a set of 3 roots. And then the last thing that we want to do is that we are going to want our roots to be ordered according to the value, because we want to know the smallest root, the second smallest root, and then the largest root. So that's pretty simple. All we have to do is use the sort function and then roots. So if you just want a quick demonstration of what that'll do, if we were to do mp.sort and then give it an array, and we'll say 3, 2, 5, obviously the order should be 2, 3, 5. There we go. So now this function is done. So now that we have a way to solve for the roots of a cubic polynomial, we have to plug in our a, b, and c that we solved for earlier when we solved for the cubic polynomial for the compressibility factor. So we're going to be solving for volume here. And we're going to be supplying pressure and temperature. And then, of course, we want VBAC, or volume. And we know that Z equals PV over RT. So V is going to be equal to Z times R times T divided by P. And of course, we want to return that. And now we know our A, B, and C. Again, these are the ones, the A, B, and C that we solved for when we solved for the cubic polynomial. So I have them written down here. The first one's just going to be epsilon plus sigma times beta minus 1. So we can go ahead and put that in. A will be equal to epsilon plus sigma times beta minus 1. Our B is a bit longer. I might just copy and paste this one to save me the typing. And you can see it's epsilon times sigma times beta squared minus beta squared times epsilon plus sigma minus epsilon plus sigma times beta plus q times beta. And then finally our C is equal to negative beta squared times our epsilon times sigma times beta plus epsilon times sigma plus q. And then of course we have to define our epsilon, sigma, beta, and q here. So we know that q, or actually we'll start with beta. Beta is going to be equal to B times P, or B times pressure. And again, these are the B and the A that we solve for all the way up here with their cubic ABES equation. So we're going to be bringing that in a second. And then divided by R times T. And then Q is going to be equal to A divided by B times R times T. And that should be a capital R, and there should be a B there. Quick correction here, this will actually be equal to Z. I got a bit mixed up. In this equation up here, we're solving for the roots of Z, and so we want to plug that Z into this equation down here to solve for our specific volume. So a quick recap of what this is going to do. We're going to give it a pressure and a temperature, and then from there it'll solve for A, B, epsilon, and sigma using this equation we defined all the way back up here. And then using that A, B, epsilon, and sigma, it can calculate beta and Q. And then using the cubic polynomial for the compressibility factor that we calculated earlier, we can plug in epsilon, sigma, beta, and Q, solve for A, B, and C of the compressibility factor equation. And then using that A, B, and C and this equation that this function that we defined up here, it'll return either 1 or 3 roots of Z, and we just have to plug each of those roots into our formula for volume here. And there we go. We have our specific volumes, and we can use them to plot our Maxwell construction. So now we're ready to try and use this. A few quick notes before then. I did forget another set of parentheses here. And then all the way back up here, there was an interesting error that I got back down here, because I had forgotten to include 2 sets of parentheses around this minus a divided by 3. So this function up here didn't actually know that minus a divided by 3 was part of this roots formula. And then that gave me a whole host of errors down here. So make sure you include that if you decide to split up the lines like I did. So we can go ahead and try this. And if we want to try this at a pressure of 1E7 pascals, and it'd help if I got that. I'm just really struggling with parentheses today. If we got this at a pressure of 1E7 pascals and 600 Kelvin, these are our 3 specific volumes. And again, these correspond to this point, and this point on our Maxwell construction.